5.2, and then we'll do the first example. So for 5.2, now we're getting into integration. And so the first thing we're going to talk about are definite integrals. Now we're gonna really hammer hard on this the formal notation and the formality of calculus, because up to this point we've been kind of informal, because basically what we want to do is just kind of get the gist of the math part of it, and then we're going to go back and look at all the notation and what it means. And so the first thing that I want to talk to you about is the concept of an integral. So I said if I have a function like this, that I can calculate the area under the curve by some sort of approximation method. Okay? And that approximation method kind of looks something like this. Well, first of all, let's talk about how we find that. Now, what I showed you on Friday, and I didn't really, I tried to do it informally, but today will be a little more formal. I showed you Riemann sums. Now, Riemann sums are of f on the interval from a to b. And so the notation of that would be okay. So C is some number value in between A and B. And basically what we do is we take this area under the curve that I have in red, and we break it up into little rectangles. And then at some point in time I'll show you how we do trapezoids. And eventually what we'll do is we'll do trapezoids with such as, well, delta x will eventually approach 0. But these little rectangles that we have here under the area under the curve, remember that the area is really just like the base times the height, right? And we said that the base is actually f of x sub n, right, times whatever we determine delta x to be. So it's the same thing. And so this summation notation, the area under the curve, the Riemann sum is the area under the curve using summation notation by adding up all of the rectangles, okay? So now what we're leading into is that summation, if I let delta x approach 0, we would call it a definite integral. So a definite integral of f on AB for any partition P, we're going to choose or let there be some value ck trapped on the interval, and all the formal stuff is listed in the thing. Then we say there exists a number I such that the limit as that partition approaches 0 is our definite integral. So now the formula with definite integral, indefinite integral, antiderivative, those all kind of mean the same things, but they have different applications. we have a function, we take the derivative. The derivative helps us to calculate the tangent, the slope of the tangent line at a point. Okay? But the derivative itself is a function. The antiderivative of a function itself is a function, or it produces a family of functions because we have to tack on the plus c. But a definite integral is where we plug in all the numbers and we actually get a numerical value for the area under the curve through this process. And if we let the partition approach 0, in other words, we're going to let the partition, the delta x approach 0, then we'll get an exact value. Now, can I move on to the next screen? Does anybody have any question about the notation? I jotted down a few things. If you wanna write down the full formal definition, I don't know. I just didn't want to give you guys carpal tunnel because it's on page 276. You should know that formal definition. In fact, I might give you a quiz on some of these formal definitions for those of you that are going to take the exam to make sure that you know and understand it. So now there's a couple of things. There's a lot of things. This definite integral I, there's a couple of things you need to know. It needs to be on a continuous function. So we'll say a continuous function f, and it has to be continuous from A to B. And if it's partitioned, and I'm really going to abbreviate this definition is also into n subintervals such that delta x, such that delta x is equal to b minus a divided by n. Now I didn't get into the formality on Friday because I wanted you guys to kind of digest the concept. But there's formulas for everything where we can calculate the exact values of, say, x sub n or delta x to whatever we want. Well, the definite integral is given by Now, that's another way to say the same thing. What I'm really saying is I'm going to get infinitely many rectangles, which means that my delta x approaches infinity. So as soon as you write this down, this is very informal. I'm trying to bridge the gap. We're going to eventually, at some point in time, in the next 2 or 3 weeks, Mr. Adams is going to write a lot of formal definitions on the board, a lot of formal vocabulary terms. That's a good chunk of determining what you need to do and when you need to do it. If they say find the integral or definite integral, you know you're going to have to find a number. If they say integrate, that's a little bit different. If they say take the antiderivative or write down the antiderivative, that's a different term. And so the terminology that they use basically will kind of tip you off to as to what you need to do when you need to do it. But basically what this is saying is, let's draw a picture and talk about it. I've got some function here, and f of x looks like this. And we want to integrate this thing from A to B. So my interval, there's a couple of things. Notice that it's continuous, right? So f of x is continuous on the interval from a to b. I want to find the area under the curve, which means I have to break this up into little rectangles somehow, some way. Okay? And we said that the area under the curve is equal to the base times the height, but really what we're talking about is each little rectangle is f of, now I said f of x sub n, but we'll use the notation in the book, which is f of c k times delta k, or delta x k. Now what that's saying is that we're going to arbitrarily choose some value c, trap between a and b, and those are going to be our x points that we're going to use to determine the corresponding y values to find the areas of the rectangles. Now the new thing that we're introducing is that delta x is really a minus, or b minus a all over n, but now in order to get the exact value, we want n to approach infinity, which is another way of saying delta x approaches 0. Now, if we take that approach, there's a formal notation, and that formal notation looks like this. To find the definite integral I, we would integrate. So the squiggly line is the integration symbol, okay? And a is what we call the lower limit. Technically, it's just a limit. I could write this either way. It could be the upper limit. And b, then, of course, would be the upper limit. But the way your problems are rigged up in the beginning, we'll talk about that a little bit later on once you kind of understand what you're integrating. So our end goal is to let delta x approach 0, or in other words, we want to put it into infinitely many rectangles. Because that's really what n is. N is the number of partitions, right? I forgot to mention that. N is the number of partitions or rectangles. But I'll start saying partition. Okay? And so let's look at all the terminology. You should probably write this down. Let me slide this up for you guys. This right here is the integral from a to b. Actually, the whole thing is, right? So this whole thing is the integral from a to b. The little thing on the function itself, and I'm going to try to do a bunch of different colors, but you can that right there is called the integrand. That's the thing that you're integrating. Let's try to do a different color here, green. This is the variable of integration. That's what we're integrating with respect to. Okay, and that's pretty much it. Now, when we say from a to b, that pretty much is the indefinite integral. Whenever we have values from a to b, although we could do it arbitrarily, but in other words, if they give us values for a to b, like 2 and 4 or 3 and 6, then we should be able to get a numerical value, unless there's a complication, like the function isn't continuous on a to b or something like that. We should be able to get a numerical value. So let's try one. So I did all that stuff to do this one example. Okay? So example number 1, we have on the interval from -1 to 3. And we're going to partition it n times such that delta x is equal to 4 minus n. And then they just want us to write the notation. So let me write it out. It says, well, let me say it and then we'll write down how to do it. It says the interval from -1 to 3 is partitioned into n subintervals with the equal length of delta x, which is 4 over n. Let mk denote the midpoint of the kth subinterval and express the limit. Okay? So now to do that, and this is of the function f of x is equal to 3 x squared minus 2x plus 5. So the first thing, so what we're going to do is we want to take the limit as n approaches infinity of the sum of our function times delta x. But what's our function? Well, first of all, let's just write it out. So we're going to say c sub k, right, times delta x sub k. But we want the midpoint. So we're going to arbitrarily choose some k values, or I'm sorry, some x values that we're going to plug into our function. So now, if I want to carry this out a little further, what I would do is I would probably write it like this. I would say all this stuff, limit as n approaches infinity of k equals 1 to n. But this is what I'm evaluating, so I'm going to say 3 times some quantity, and we're going to leave that blank for a second, minus 2 times some quantity, leave that blank for a second, plus 5. That's our f of whatever we choose to plug in. Times what? Delta x. Okay? Now if we choose the midpoint, I think we talked about this when we talked about the rectangular approximation. We said maybe we could choose the midpoint. I might change the notation a little bit to m sub k. Okay? Now all that means is that my starting point and my and so let's like kind of draw the graph of this, okay? What we're trying to do is that our function f of x kind of does one of these deals over here. And what we're looking for is if I draw a rectangle, I'm looking for this m, the midpoint of the partition. So delta x is still delta x, and how we find the delta x and the base doesn't change. The only thing that changes is the height. Where do I calculate the height of the rectangle? So normally, like I might start with -1. Like if I were to put this into, say, 4 partitions, my first x value would be 1. And it would go from -1 to 0. And then 0 to 1, and then 1 to 2, and then 2 to 3. But instead of plugging in -1, I might go in the middle of -1 and 0. So I would plug in -0.5. Does that make sense to you guys? All right. So to denote that it's going to be the midpoint, we're going to say mk. And then how we plug it in later, I'll show you. So now, this is the same thing as what's our lower boundary? This is like a comma b. -1 to 3 of our function f of x, which is 3x squared minus 2x plus 5. Now, we say times delta x, or dx.